So we are discussing integration of non-negative simple measurable functions. So we recall the definition of integral of a simple non-negative measurable function. Okay, the function is simple if it has only finitely many values. Namely, we take alpha 1, alpha 2, alpha n. Okay, the integral of s with respect to mu is defined by alpha k mu ek, where ek is the inverse image of alpha k, right? S inverse of alpha k. Okay, this is a definition of integral of s. Okay, we proved the theorem that suppose s is a non-negative simple measurable function and phi is a set function defined on the sigma algebra A into minus infinity gamma infinity defined by phi of E equal to integral over E s d mu. Then this phi is a measure on x. Okay, this theorem we already proved in the last class. Okay, in this class we continue to discuss the integration of properties of integral of simple non-negative functions. Suppose let's s and t be two non-negative simple measurable functions. Non-negative simple measurable functions. Then integral over x s plus t du. Again, sum of two simple non-negative measurable function is again simple. The sum of two measurable function measurable. So s plus t is simple non-negative measurable function whose integral is sum of the integral of individual two non-negative simple measurable functions. Okay, this is the natural property we have already seen in the Riemann integration. Okay, let us fix the values of s and t and corresponding partition of x. So let us take alpha 1, alpha 2, etc., alpha n, and beta 1, beta 2, etc., beta m be the values of t, s and t respectively. The set Ea equal to inverse image of alpha I for I from 1 to 3, etc., n, and set Fi equal to index difference index Fj equal to T inverse of beta j. Okay, j from 1 to 3 up to m. Okay, then by the definition of simple non-negative measurable functions, integral over x s d mu is summation I from 1 to n alpha I measure of Ei, and integral over x t d mu is summation j from 1 to m beta j measure of ft. Okay, this by now the function s plus t has values. Right? S plus t is by the definition of sum of two functions s plus t of x equal to s of x plus t of x. Okay, alpha 1, alpha 2 are values of s of x, beta j is value of t of x. So s plus t, okay, assumes the value alpha j plus beta. So alpha I plus beta j. Okay, I from 1 to 3 etc. n and j from 1 to 3 etc. to n. Okay, then what is the corresponding partition of x? Now we discuss. Let's Aij is a set of all x in capital X such that it's the inverse image of alpha I plus beta. So that is s of x equal to alpha I plus beta j. Okay, by the definition of s plus t, this s of x plus t of x must be alpha I plus beta j. Okay, s of x only assumes alpha I values, so set of all x such that s of x equal to alpha I plus set of all x in intersection x in capital X such that t of x equal to beta j. So this is ei intersection fj. Okay, this is the inverse image of s plus t, t alpha I plus beta j under the function s plus t. Then again by the definition of integral of simple function, integral of simple function, integral over x s plus t d mu s summation over I from 1 to n summation over 1 to n alpha I plus beta j mu of ei intersection fj. That is aij, capital Aij. Our Aij is alpha I plus beta j into Aij is mu of ei intersection fj. Now we are going to split this summation into two parts in the following way. Okay. Now now we split into two summations, summation I from 1 to n, summation j from 1 to m, alpha I plus beta j, alpha I mu of ei intersection fj plus summation I from 1 to n, summation j from 1 to m, beta j mu of ei intersection fj. Right, the same thing here. Take little backward and mu of ei intersection fj. Okay, now here alpha is independent of this second summation, so summation I from 1 to n alpha I summation j from 1 to m mu of ei intersection fj. Here summation, okay, what j can be taken out, summation beta j summation I from 1 to n mu of ei intersection fj. Okay, since the collection ei intersection fj, j from 1 to n, and also collection ei intersection fj I from 1 to n, here 1 to m index, okay, are mutually disjoint classes, okay, whose union is whole x. Therefore the integral over x s plus t d mu, the first summation is by the countable additivity of mu, okay, this second summation become the following: mu of union j from 1 to m ei intersection fj. So here if I take two different sets, they are mutually disjoint because collection fi are mutually disjoint, plus summation j from 1 to m beta j mu of union I from 1 to n ei intersection fj. So for a fixed fj, e1 e to en intersection fj are mutually disjoint. So by the distributive law we write summation I from 1 to n alpha I mu of ei intersection union j from 1 to m fj plus summation j from 1 to m beta j mu of union I from 1 to m ei intersection fj. Okay, so this is equal to summation I from 1 to n alpha I, the set will become simply ei because union fj is whole x, okay, whole space x, ei intersection x is ei. The second part j from 1 to m beta j measure of union ei is whole x, x intersection bj fj simply fj. So again, so by the definition of s, integral of s, this is integral over x d mu plus integral over x t d mu, hence the theorem, right? So okay, so we can add two integration of two functions, we get therefore integral over x s plus t d mu equal to integral over x s t d mu plus integral over x t d. Okay, so now we write the definition of integral of non-negative measurable function. So integral non-negative measurable function. Already we have seen the approximation of non-negative measurable functions by the simple functions, right? So recall the definition of the approximation theorem, that suppose f is non-negative measurable function, then there exists a sequence Sn such that 0 less than or equal to S1 less than or equal to S2 and so on. It is Sn increasing and converge to everything bounded by f, and Sn converge to f pointwise. But here from the properties of integral, right, we write the following note. Okay, in this function the relation between S1 and S2 Sn is the following: 0 S1 less than or equal to S2 less than or equal to S3 and so on. So this implies that the integral value of S1 always less than or equal to integral of S2 d mu and so on, right? This is also increasing in nature. So the limit Sn integral Sn d mu is going to be our integral of f, right? This number will be our integral of f. Okay, either you take, if I take increasing sequence, everything bounded by and f Sn converge to f, then supremum overall simple functions less than or equal to f. Okay, is that's all. Okay, so now using this, okay, note, we write the definition of integral, right? Integral of non-negative measurable function. Let's f from x to minus infinity comma infinity. Here you take 0 comma infinity be a measurable function. Here the specific non-negativity will be given there separately, be a non-negative measurable function. Okay, then the integral of f over x with respect to the measure mu is defined by integral, okay, defined by integral over x f d mu equal to supremum taken over all simple functions, right, integral f d, supremum of the set of real numbers. Integral over x is d mu, the supremum taken over all non-negative simple measurable function. The approximation theorem says that, okay, this integral is supremum of some set. This set is the set of all numbers obtained using set of all numbers as the integral of simple non-negative measurable function less than or equal to. So in this set there is an increasing sequence, okay, which converge to integral f d. That's the idea of, okay, this will hit integral f d. That's the idea. Integral s1, integral s2 and so on, it will, okay, you will hit a point, okay, it will converge to a point. That point will be defined, that point is defined to be integral of f. Okay, this is definition I take. This is one. This definition will be used in the forthcoming discussions. So this is definition 1. Okay, equivalent definition 2, equivalent to second definition. Okay, so let's f be a non-negative measurable function. Same thing, right? From x into minus infinity comma infinity be a non-negative measurable function. Then the integral of f, okay, over x with respect to mu is defined by integral over x f d mu will be limit of the sequence, limit n tends to infinity integral over x s n d mu. So what is that? Okay, where Sn is a sequence of non-negative measurable functions, simple measurable functions, such that, okay, 0 less than or equal to Sn less than or equal to f and Sn converge to f pointwise. Okay, so these two definitions are equivalent, right? Definition 1 to remark. So definition 1 and 2 are equivalent. But anyway, we use to prove that, okay, we prove this. If you are interested, you, okay, prove the result. Okay. The second definition follows from the approximation of this. Okay, f by simple non-negative measurable functions. Okay, the next properties of integral f d mu, right? That is, before writing the properties, we write the integral of f over arbitrary measurable set. Okay, let's definition 3. Okay, let f from x to 0 minus infinity infinity be a non-negative measurable function. And E is any measurable set. E is a measurable set. So measurable set, it's a members of simply members of A, right? That is members of A. Then the integral define the integral of f over E with respect to the measure mu is defined by the following. Defined by integral over E f d mu. Okay, this is supremum. Integral over E s d mu already defined. Okay, the values of all s d integral over E s d mu, take the supremum taken overall simple functions less than or equal to f. Okay, so now we should write the properties of integral f. Okay, the first property, okay, if we assume that f is non-negative measurable function on x. Okay, if c greater than or equal to 0, then we know that it's a constant multiple of a measurable function is measurable. Okay, so now we are going to compare the integral of c of d, okay, and the integral of f. This will be c times integral over x f du. Okay, the second property, okay, if E is measurable, then integral over E f d mu can be compared with the integral over x. Okay, you take integral over x f d mu, but outside E, the f, if f function is 0, then you can include all the points. So we can multiply the characteristic function to make the, okay, value of outside of E to be 0. So this is d. Okay, and the third one, if f equal to 0, if f is identically 0, then integral over E f d mu is 0, even if measure of E is infinity. Okay, and the fourth property is if integral over E s d f d mu, okay, sorry, this, if measure of E is 0, if measure of E is 0, then integral over the set E is 0 for any non-negative measurable function. Okay, these are the properties of, there are so many properties, we will see one by one. Okay, the properties of no problem. Okay, first property, it's a very simple property, right? Just in the properties, let me definition of integral, simple function integral use பண்ணி தான் பண்ண போறோம். Okay, proof என்னன்னு பார்க்கலாம். Okay, first part of, we start with integral of c of dv, right? By the definition, this is supremum over, okay, in what follows I am going to use only definition 1, s d mu, where simple functions taken overall CF. Okay, and also you write the integral of f as supremum taken overall s dash simple functions, the s dash less than or equal to f. Okay, there are two integrals we have. Now we are going to prove that first one is a constant multiple of second. Okay, so to prove that we compare the simple functions less than or equal to CF and the simple function less than or equal to F. Okay, if we have one-to-one correspondence between these two, then these two will be same, right? So let us take S be a simple function such that 0 less than or equal to S less than or equal to CF. Then define S dash equal to S by C. Okay, so function S divided by the constant non-negative constant. Then S is a S dash is non-negative because C non-negative, S of x value non-negative. So S dash is non-negative. Leah is non-negative. And S is simple function, so constant multiple is simple function. Okay, simple, and also it is measurable function. Okay, what about the range of S? Such that, what about S dash is non-negative, which is equal to S by C. Okay, but S is less than or equal to CF, so this is less than or equal to CF by A. See, this is for the discussion C equal to non-zero. So here I am going to write the case 0 over now. If C equal to 0, the result is trivial, right? The result is trivial. Result is trivial, and we assume that C is non-zero. Assume that C greater than 0. So for the discussion C greater than 0, we will do this. Okay, and C is cancelled, so S dash is less than or equal to F. Okay, so this implies integral over S dash d mu is less than or equal to F. So S dash is a part of the supremum second definition, right? Okay, this is equation 1, this is equation 2. So every S, okay, such that 0 S less than or equal to CF, there is a simple non-negative function S dash less than or equal to F. Okay. Right? This is 4x. And conversely, if I take, if S dash is a simple function, non-negative simple function, simple measurable function, such that 0 less than or equal to S dash less than or equal to F, by taking S equal to, S equal to CS dash, then S is a simple measurable function such that 0 less than or equal to s less than or equal to cf. So the functions, simple function accommodated in equation 1 and 2 are equal to. So therefore every s appearing in the first equation can be written as for every s in equation 1 every simple function s in 1 can be expressed as s equal to cs dash for some simple function s dash in 1. For every function s dash appearing in 1. For every simple function s dash in equation 2 and vice versa. And conversely right, so conversely. Okay, so this is the thing. So therefore every s in s dash, s in 1 will be cs dash, and every s dash in 2 will be s by c dash. Therefore s d mu can be written as integral cs dash d mu by the definition c times s d mu in 1. So therefore integral f d mu equal to supremum over all 0 less than or equal to s less than or equal to cf s d mu can be written as supremum over integral cs dash d mu, where s dash taken over all f. So one-to-one correspondence between these two sets for which supremum calculated. This is the supremum c times something. C can be taken outside because it is positive. Integral over s dash d mu 0 less than or equal to s dash less than or equal to f. So this is integral f d mu. This is all. Now prove the second result. That's very simple because one thing you write here is integral over e f d mu is, with the definition, this is integral over e s d mu 0 less than or equal to s less than or equal to f. Now define s dash equal to s times characteristic function e. It's a simple function. Clearly 0 less than or equal to s dash less than or equal to f characteristic function, and vice versa, right? Therefore integral over e f d mu is written as supremum integral over x s d mu again characteristic d mu, right? Where 0 less than or equal to f s less than or equal. This is because of this is by the property of integral s du, right? Already we have seen, and in the place of s you write characteristic function. So supremum overall integral over x s characteristic function e d mu for 0 less than or equal to s. Okay. In the place of s characteristic function you write s dash is also equal to supremum interval over x s dash d mu 0 less than or equal to s dash less than or equal to f characteristic function e. Okay, so this is equal to interval over x f characteristic function e d mu. Third part, okay, if f is identically 0, then okay, any simple function, simple measurable function such that 0 less than or equal to s less than or equal to f is identically 0. That is interval over s d mu interval over x s d mu is 0 for all s such that 0 less than or equal to s less than or equal to. Okay, so taking supremum over all simple functions, we have taking supremum over all simple functions such that 0 less than or equal to less than or equal to implies interval over x f d mu will be 0. So next case, next one, if measure of E is 0 or set to the measure 0 na interval over the set f d mu is 0 as a proof. Yeah, the set to the measure 0. If let us take s be a simple function, okay, simple measurable function such that 0 less than or equal to s less than or equal to f, then interval over s interval over x d mu over e, right? Okay, d mu is, by the definition, it is written as alpha 1 measure of E intersection EI by the definition. Here you write the values of, and let alpha 1, alpha 2, alpha n be the values of yes. Then by the definition you write this, but measure of E is 0, so all the subsets, if the subset of E is measurable, then its measure also 0, so this is 0 because the following E intersection EI is subset of E, so measure of E intersection Fi is less than or equal to measure of E, but this measures 0, right? So this also has measure 0, E intersection E. Okay, now so we have come to that statement that interval over E s d mu is 0 for all simple function such that 0 less than or equal to s less than or equal to. Okay, so in taking supremum over all simple functions, taking supremum over all simple functions such that 0 less than or equal to f, we get integral f d mu. All the integral simple functions less than or equal to f has integration 0, so supremum also 0. Okay, so integral over any set of measure 0 is 0. So integral, okay, the statement is this: the integral of any non-negative function f, non-negative measurable function f, over assets of measure 0 has value 0, is 0. The integration value is 0. Okay, this is most important result. Sometimes we can suppose we have situation like this. Suppose E union f d mu. Suppose integral over union of two sides can be written as integral over E f d mu, okay, if measure of f is 0. So those sets having measure 0 can be taken out of, right, can be taken from, okay, out from the integration process. And then now we prove very important theorem. State the theorem. Next day we will prove that theorem, right? Okay, the theorem is Lebesgue monotone convergence theorem. So the theorem statement is the following. So let's Fn be a sequence of non-negative measurable functions okay on X, okay, such that number 1 0, it's non-negative but it is monotone, right? Yes, f1 of x. Now we write the domain and the codomain of fn, that's most important. So I'm going to take this to the next page. Simply non-negative measurable function. Fn less than or equal to f2 less than or equal to, and so on. So everything less than or equal to f. Right? Means what? That is for all x in capital X, f1 of x less than or equal to f2 of x less than or equal to, and so on. Everything less than or equal to x, right? Second condition, okay, yes, Fn converge to f pointwise. Okay, pointwise convergence on X. Okay, so that means for each x in capital X, Fn of the sequence of numbers converge to f of x. Okay, this is a pointwise convergence. Then the conclusion part is very important. We know, we have studied that if a sequence of integrable function, Riemann integrable functions converge to a limit uniformly, then integral fn converge to integral f. But here point-wise convergence with monotonicity is enough for the convergence. So conclusion, integral over x limits n tends to infinity f and d mu is integral over f d mu. Okay, so Riemann integration limit convergence வந்து ரொம்ப மாறுபடும். எந்த விஷயத்தில் பாயிண்ட் வைஸ் கன்வர்ஜென்ஸ், இந்த பாயிண்ட் வைஸ் கன்வர்ஜ் ஆகும், மோனோட்டானாகவும் இருந்தால் ரைட். யூனிஃபார்ம் கன்வர்ஜென்ஸ் இருந்தால் தான் ரீமான் இன்டெக்ரல் ஓகே சீக்வன்ஸ் ஆஃப் ரீமான் இன்டெக்ரேஷன் வேல்யூ ஆஃப் ரீமான் இன்டெக்ரல் வேல்யூ கன்வர்ஜ் ஆகும் இல்லையா. சப்போஸ் fn ரீமான் இன்டெக்ரபிள், integral fn converge to integral f when fn converge to f uniformly. But here in the case of Lebesgue integration, okay, யூனிஃபார்ம் கன்வர்ஜென்ஸை ரிலாக்ஸ் பண்ணிவிட்டு மோனோட்டான் சீக்வன்ஸாக இருக்கணுன்ட்டு நம்ம ஸ்மால் காம்ப்ரமைஸ் எடுத்துக்கிறோம். ஓகே ஓகே, இந்த ப்ரூஃப் அடுத்த கிளாஸில் பார்ப்போம். பட் இந்த ப்ரூஃபோட ஐடியா என்ன அப்படின்னா, ஓகே, ஐடியா ஆஃப் த ப்ரூஃப், ஐடியா மட்டும் சொல்லுங்கள், ஐடியா ஆஃப் ஓகே ப்ரூவ் பண்ண வேண்டியதுன்னா லிமிட் fn ஈக்குவல் டு இன்டெக்ரல் f அப்படின்னு சொல்லுங்கள். லிமிட் இன்டெக்ரல் இப்போ ஆல்ஃபான்றது என்ன எடுத்துக்க போகிறோம்னா லிமிட் ஆஃப் திஸ் ஓகே ஆல்ஃபா ஈக்குவல் டு லிமிட் ஆஃப் f and d mu. ஓகே, ஸோ ஆல்ஃபா ஈக்குவல் டு லிமிட் fn integral fn d mu n tends to infinity integral fn d mu. லெஃப்ட் ஹேண்ட் சைடு ஆல்ஃபான்னு எடுத்துட்டா நான் என்ன ப்ரூவ் பண்ணணும், ஆல்ஃபா ஈக்குவல் டு இன்டெக்ரல் f d muன்னு ப்ரூவ் பண்ணோம். 2 கேசஸாக ப்ரூவ் பண்ண போகிறேன். எப்படி, ஒன்று ஆல்ஃபா லெஸ் ஆர் ஈக்குவல் டு இன்டெக்ரல் f d mu ப்ரூவ் பண்ணணும், இன்னொன்று ஆல்ஃபா கிரேட்டர் ஆர் ஈக்குவல் டு இன்டெக்ரல் f d mu ப்ரூவ் பண்ணணும். ஆல்ஃபா லெஸ் ஆர் ஈக்குவல் டு f d mu இல்லையான்னு பார்க்கணும் இல்லையா. ரைட், இப்போது f1 f2 fn இருக்கு இல்லையா, இந்த ஃபங்க்ஷன்ஸ் இதோட இன்டெகிரேஷன் எப்படி இருக்கும், இன்டெக்ரல் f1 லெஸ் ஆர் ஈக்குவல் இன்டெக்ரல் f2 லெஸ் ஆர் ஈக்குவல் டு இப்படி இருந்தால் இந்த சீக்வன்ஸ் எங்கே ரைட், இப்படி இருக்கும்போது ரைட் எல்லாமே எதை விட சின்னதாக இருக்கும், இன்டெக்ரல் f d mu விட சின்னதாக இருக்கும். அப்போ இதோட லிமிட்டும் எதை விட சின்னதாக இருக்கும், ஆல்ஃபாவோட இன்டெக்ரல் f விட இருக்கும். Okay, if all the function integration values are less than or equal to integral f d mu, right, then alpha less than or equal to integral f d mu. So alpha less than or equal to integral f d mu prove பண்றதுக்கு when f1 less than or equal to f2 we prove integral f1 less than or equal to integral f2, right. இந்த function inequality இருக்கும்போது integral value இந்த அதே மோனோட்டான் இருந்ததுன்னா ஓகே alpha less than or equal to f d mu ன்னு சொல்லிடலாம், right. அதுவே alpha greater than or equal to integral f d mu சொல்லணும்னா fn integral fn converge to this இல்லையா. அப்போ என்ன சொல்லணும், ஆஃப்டர் certain ஸ்டேஜ் integral fn வந்து integral f விட அதிகமாக போகுது அப்படின்னு சொல்லணும், ரைட். அது சிம்பிள் ஃபங்க்ஷன் வழி எழுதப்போம். இன்டெக்ரல் நம்ம ப்ரூவ் பண்ண வேண்டியது என்ன, இன்டெக்ரல் f d mu less than or equal to alphaன்னு ப்ரூவ் பண்ணுறதுக்கு இப்போ இன்டெக்ரல் ஆஃப் f d mu என்ன, சுப்ரீமம் integral f d mu s d mu less than or equal. இந்த கலெக்ஷன் இருக்குல்ல, இதோட லீஸ்ட் சாரி கிரேட்டஸ்ட் லோயர் பவுண்டு தான் இன்டெக்ரல் f. அப்போ இந்த ஆல்ஃபாங்கிற நம்பர் பெருசுன்னு சொல்லணும்னா அது ஜஸ்ட்டு அப்பர் பவுண்டு சொன்னால் போதும் இல்லையா, ரைட். இது லீஸ்ட் அப்பர் பவுண்ட், லீஸ்ட் LUB, இது LUB ஓகே. இது LUB விட ஆல்ஃபா பெருசாக இருக்கும்னா ஆல்ஃபா என்ன சொன்னால் போதும், அப்பர் பவுண்டுன்னு சொன்னால் போதும். எதுக்கு, இன்டெக்ரல் s d mu. அதனால் நான் ஒரு s எடுத்துக்கிறேன், இந்த மாதிரி இன்டெக்ரல் f s d mu லெஸ் than or equal ஆல்ஃபான்னு ப்ரூவ் பண்ணுறேன்னா ஆல்ஃபா அப்பர் பவுண்ட் ஆகிடும், ரைட். ஓகே, இப்போ இதுதான் ப்ரூவ் பண்ண போகிறேன் நான் அடுத்த கிளாஸில். ஓகே, இதை ப்ரூவ் பண்ண s வந்து அப்பர் பவுண்ட் ஆஃப் சாரி ஆல்ஃபா இஸ் அப்பர் பவுண்ட் ஆஃப் திஸ் செட்னு ப்ரூவ் பண்ணுறேன்னா இது ப்ரூவ் ஆகிடும். ஓகே, இது மட்டும்தான் லிட்டில் ஓகே காம்ப்ளிகேட்டடாக தெரியும், பட் எனிவே நான் லாஸ்ட் கிளாஸில் ப்ரூவ் பண்ணேன். ஓகே.